Edoardo Paolo Scalafiotti with high-performance Go code. But before giving him the microphone, I would like to recommend you to take a look at your email and go to the feedback form and compile it in order to help us improving the conference for the next editions. Thank you very much.
Hey guys, so being the last talk, I'll keep it very, very short. I have just like 100 slides, so it's fine, some code. No, I mean, I'll keep it short. So, okay, so I have to show this because a lot of the slides are taken from the big guys, Bob and Matt Ryer and Dev Cheney. So you can mix, do whatever you want, sell whatever. And everything is on Medium and also on GitHub. So a little bit about me, about the company that I work for. So I work for Sainsbury's Supermarkets, which is a huge retailer, one of the biggest in the world, the second or third biggest in the UK. We have 27 million transactions per week, so it's a lot, offline and online. Our offline system, so the cash system, etc., they run also on a similar online architecture. So we have, if anything goes down, it's a very huge problem. We have over 30,000 products, even though on one supermarket we had 300,000 different types of products. So it's like huge catalog. 1,200 stores and one online fulfillment center, which is basically it's awesome. It's like basically a supermarket where just colleagues they do the groceries, and it's just for online fulfillment. It's huge. It's a 120 million investment, and it was just for one part of London, so it doesn't serve even all of London. And we have over 82,000 colleagues. Just as a reference, we have load balancers for internal tools, so it's like a huge system. But okay, so as developers and as engineers, what do we do at the core? At the core, we are Defying nature. This is, I will make a point at some point, so don't you worry, just follow me. So this one is the Bugatti Veyron. You probably all know it. It's able to reach speeds of 428 kilometers per hour. In all currency is 250 miles per hour, I think. And it's fine, it's dandy, you know. It's like, okay, so what's the point? You know, it's like it's just fast. You know, you just add horsepower, and it just goes faster. But it's not the case because you don't just add speed to something to make it faster, because unfortunately nature has some rules. In this case, this is the drag formula, and u is basically a velocity. So that means that when you increase the velocity, velocity increases its squared. So that means that the drag is very hard. So from 400 and 410 kilometers per hour, you need to add 100 horsepower. So it's like huge. That means that nature has some limits. And we try to defy them, but it's not that easy. Okay, so the point that I'm trying to make is this one. This is a modern CPU. We are trying to make them faster, but it's not easy. And in the last years, we have reached a limit. And this limit is basically that is this one. So every year we doubled. This is more slow, right? So every year we doubled basically the power, and we continue to shrink our CPUs. The only problem with that is that in 2015 we basically reached a limit on the size of our CPUs. And in 2005 we basically reached the maximum number of CPU cycles that we can have, so of gigahertz basically. So that means that by 2005 we reached 4 gigahertz CPUs. By that rate, by now we should have had 20 gigahertz CPUs. The only problem is that from 4 gigahertz to 5 gigahertz, we need like very cool, very high tech cool systems and stuff. So basically, 5 gigahertz is very, very hard to find. And don't be deceived by the size of the CPUs. We cannot shrink it more. That means that we are defying some physical laws at the moment, because electrons, when you have like very, very tiny wires, electrons they like to go in a quantum way, so they like to behave in a quantum way. So it's very, very hard. So that means that we've reached basically a limit. And so that means that basically the free lunch is over. But better yet, the free lunch was already over in 2005. And right now we're starting to pay for it. Where is the free lunch? Here, okay. But the free lunch is over is basically was a paper by Herb Stutter, published in the Other Job journal back in 2005, and basically said that the state of the art of innovation was in CPU was basically stopped because the Moore law applied to clock speed had stopped, as did the total performance per clock and overall power. So basically, the future back then was, again, yeah, we should have had faster CPUs. So the future in 2005 was, okay, so let's add hyper-threading, let's go multi-core, and let's build caches, right? Caches were built on the CPU, so we've had L1 caches. Every 10 years, basically, we have a new cache. So L1, L2, L3, and we're now looking at L4 caching. We've done that. Right now, we have the i7s. The latest one, the KB Lake, has all of these things. So the future right now is basically mostly about architecture, so improvements on the architecture, out-of-order execution, speculative execution, so basically it tries to do something before that the memory is actually allocated, so it's like very interesting, very weird, and vector SSE instructions. SSE instructions is also the latest update, one of the latest of the update of Go 1.7, and for x86-64 architecture, and on Go 1.8, it's for every architecture. So basically, when you talk about this one, is like very, very high level optimization. And I don't know, what is the future? The future could be maybe, do you know what this is? Have you ever heard of HP is the Machine? Someone has heard of it. So basically, it's a new system, it's a new machine. And it uses photons to communicate. But most of all, it's like it has several cores of CPUs, and it has a huge amount of memory, like a lot of RAM, like terabytes, lots and lots of terabytes. And it's modular, so you have racks. It's for servers, of course. You have racks with all these things. The interesting part is that the CPU can directly access the memory with photons, so it doesn't use electrons but photons. But when you add more racks, a CPU here can actually access a memory down there directly. So it doesn't need server-to-server communication. It's like direct. And so it's like a huge change. Right now, it's like it's an experiment, so we'll see where it goes. So the free lunch is really over. We cannot increase the power of, not a lot at least, of computers. And so what can we do to sell more devices and to keep doing what we're doing and to keep processing high data and all the IoT devices that we're basically using? And by the way, why do we need high performance anyway? In my opinion, high performance at the moment is very important because we have a microservices architecture that is very common right now. Microservices it has a lot of network latency, so it's very hard to do it in a not compiled language. So you can do it in an interpreted language, but it adds more time. So it's not very performance. We have IoT devices, which are very, very small. And so it needs compiled languages and therefore high performance. And maybe in the future, mobile devices that wants to keep an eye on full convergence. So basically, full convergence is that I run basically an operating system on my phone. I use it as a phone. I arrive at home. I plug it on my desktop, and it becomes my computer. So basically, this becomes my only computing machine. And this computer, for example, already has something like that. You just plug an external graphic device, and it runs as basically a gaming rig laptop. So we're already getting there. Also, serverless. Serverless is something, well, I think all of you have seen it, have used it, but basically, high performance in serverless is translated exactly to cost. So high performance is like you diminish your cost. And then massive P2P, so like blockchains. This is especially important. I've received lots of comments about something that I've said about blockchains, where you see a lot of users using, for example, Python or Ruby or Java for these kind of things. And this becomes very, very hard to explain because if I have a miner that I run at home or even on my computer, and I'm running a miner on Java or something like that, it beefs up my CPU. And maybe I want to use my computer also for something else. So it's not really good for my community to have something that is not very optimized and high performance, in that case with P2P technologies.